Together 2026. I want to welcome Sophie Morel to speak to us about Nori's construction and lean. Thanks.
Yeah, thanks for the invitation. So I guess this is going to be a more straightforward formalization talk. So I'm going to tell you another story of how I failed to formalize something. It's Nori's construction. So, well, let me show you a theorem first. So if it looks intimidating, I'm going to explain a little bit the terms, and the theorem statement is going to I'm going to show it several times. So it's a theorem about some universal constructions in category theory. Okay, so I should say it's originally a less general form of that is due to Nori. Here I'm quoting this by Viali and Prest, and because they have the best statement as far as I know. But if you know a little bit about category theory, and if you heard me talk about formalizing category theory, you know that I'm going to complain about the way this is written. A lot of these are lies. This equality is a lie. This equality is a lie. This is not really what I want to talk about today, but just to remark on that. Anyway, so why was I interested in this? So this is basically this is the basis of a whole theory, which is called the theory of Nori motifs, and I've done a bit of work on Nori motifs in my non-formalization life, and in particular I have a paper with Ivora about something called the 6 operations, which is a technically quite complicated paper, and I was trying to simplify some parts of it using ideas from another mathematical paper, and I'm not going to name the author because I don't really have good things to say about the other paper, and the point is not to shame anybody. And as I like to do, I like to when I have constructions in my papers that are a little bit complicated, abstract nonsense, it's easy to miss a mistake in them. It's nice if you can formalize them. So you feel a bit safer about them. So I was trying to do that. And there were a few problems with that. And the first problem was, well, you can see the slide, mathematical. So the paper I was trying to use, actually I don't think it's correct at all. So yay. I don't think it's fixable. Yay. And then I also ran into some trouble with the formalization, which is what I want to talk about today. Okay, so coming back to the theorem, it has two parts, and I'm going to concentrate on the first part. So let's just talk about the second part very briefly. So the second part is something about abelian category, Serre quotients, blah blah blah, and this is basically the statement you can write using the current version of MathLib. You cannot prove it, but you can prove it modulo a few stories, and I'm very happy to put stories for anything that has a nice proof in the literature. So I'm happy enough with the second part. Okay, so now maybe I'll start explaining some things. So this is the first part. So it says if you have a quiver, basically there is some kind of there's some kind of free abelian category on the quiver. Okay, and I promised I would try to explain a little bit what all of this means. So let's go back a bit. So what is a quiver? A quiver is just an oriented graph, so it has vertices and it has arrows between the vertices. And yeah, I don't think I can draw here. Just oriented graph, so you can have several arrows between the same two vertices. You can have an arrow just looping, so going from one vertex to itself. And in Math and also in MathLib, the vertices are actually called objects, and the arrows are called hobs or homomorphisms. And each arrow, so the only rule is each arrow has a source and a target. Okay, and a category is a quiver where you can compose the arrows. So if you have two arrows that are composable, so the target of the first arrow is the source of the second arrow, then there is a composition, which is an arrow that the source is the source of the first arrow, the target is the target of the second arrow, and then you want this composition to be associative, and you want to have identity arrows that are identity for the composition. Well, the basic examples, if you have some kind of object with some kind of structure, those are the objects, and then the arrows are the maps that preserve the structure. So like groups with morphisms of groups, abelian groups with morphisms of groups, topological spaces with continuous maps, etc. Okay, and then you can add some structures on categories. So I was talking about abelian categories, but before that I have to talk about what it means to be an additive category. So first there is something called a pre-additive category, and that means that the sets of harms with fixed source and target are abelian groups. So you can add arrows that have the same source and target, and composition is additive in each variable. So for example, the category of abelian groups is pre-additive. So the reason I put this very contrived condition on the rank is that the category of abelian groups actually is all the way down on the slide. It's an abelian category, and I wanted to have an example of each type that was not an example of the next type. An additive category, it means that you have direct sums. So direct sums, if you don't know, I mean, so for, I think basically every object you can think of is the usual direct sum, and then there is a definition that only involves the category structure that I'm not going to write. And for example, the category of abelian groups is additive, but also if you take the category of free abelian groups, well, the direct sum of free abelian groups is free, and so that's also an additive category. But it's not what the next thing is abelian. It means that you also want to have kernels and co-kernels, and well, images, and something called co-images that we don't really worry about in usual mass in abelian categories, and that they should behave in a nice way, like the way you would expect for example, the category of abelian groups. So again, I don't want to spell out all the axioms, just to give you an idea. So basically you start with just vertices and arrows, and then you add structure, you add structure, you add structure. And the theorem, it says that you start with the thing that has the least structure, the quiver, and then you can build this abelian category, which is like a free abelian category on it. And I'm saying structure, but actually, well, going from quiver to category, you add structure. Going to pre-additive, you add structure, but after that, you're not adding. You're adding conditions actually. So it's a little bit of both. Okay, and then you have, well, there was also something about the functors. Actually, it was called representation here because I was using the vocabulary of Nori. So you have a notion of morphism of quivers, which is just something that sends vertices of the first quiver to vertices of the second quiver. It sends arrows to arrows and respects source and target. So this is called a representation. It's called the morphism of quivers, and in mass-lib it's called the pre-functor because we think of it as, well, functor with fewer properties. If your quivers are categories, then a pre-functor is called a functor if it respects composition and identities. And then if you add the structure, for example, pre-additive categories, your functor is called additive if it respects addition on arrows. If the categories are abelian, the functor is called exact if it respects kernels and co-kernels. So I didn't mention direct sums because an additive functor automatically respects direct sums when they exist. Just a heads up. So I think I've defined all the terms. So here's the theorem again. Yeah, my slides are basically 5 slides that I keep repeating. This one, I think, is the third time we see it. I don't remember. Okay. So, well, I think I've defined every term in the theorem now. And so the theorem, again, I should say it's a lie. The way it's written, it's actually not correct because it's stating that there exists an object with a universal property, but we are working with categories, so it's a two universal properties. So this thing, the uniqueness statement, the functor is not actually unique. It's going to be unique up to a unique isomorphism of functors. The diagram here is not actually commutative, it's commutative up to isomorphism. If you want to state the theorem correctly, you have to be a little bit careful. I just wanted to give you an example of how these things are stated in the literature very often. Okay, so now let's talk about the proof. So the proof is, a big chunk of it is in MathLib, actually. So the idea is that you're starting with this quiver, and then you're building these three objects on it. You're adding the structure, category, pre-additive category, etc. So the proof you do in several steps. You start with a quiver, and you construct what is called the free category on the quiver. And this is in MathLib, it's called the category of paths. And the idea is just that you just freely add compositions of arrows. So arrows in the free category are just paths in the quiver. Composition is concatenation of paths. And then you make the pre-additive category on this, which is also in MathLib, is called category theory.free. The Z, because we're using Z coefficients, is just, well, you want the Hom sets to be abelian groups. They are not abelian groups. You replace them with the three abelian groups on the Hom sets of your category, extend composition by linearity. And when you have a free pre-additive category, for it to be an additive category, you need direct sums. Maybe you don't have direct sums, just formally add them as new objects, and then the morphisms between direct sums are matrices. So this is also in MathLib, it's called, well, category theory mat underscore. And the last step is when you have an additive category, you have to freely add kernels and co-kernels. This is not in MathLib. So that was the step that was left. Okay, I should check time. Good. Okay, so here is actually correct definition of the free abelian category on an additive category, where I gave a definition where actually you don't say for every functor from A to B there is a unique functor, blah blah blah. You actually state it as some equivalence of categories between functor categories, but it's the same idea, modulo a few technicalities. And this has been known for a long time. And so the construction is due to Freud, and the construction is quite simple. You just formally, it goes in two steps. Formally, you start by adding co-kernels, so you have your additive category. You can embed it into an abelian category. You just take the category of additive pre-sheaves, so additive functors from C up to the category of abelian groups. You take the image of C by the Yoneda embedding, add all co-kernels of maps in this image, check that the category you obtain has co-kernels, and then you just dualize this construction. So here you added co-kernels, then you do this dualization, it adds kernels, and you check that this did not destroy co-kernels. Okay, then so I tried to do that in Lean. It was horrible, absolutely horrible. I think it might be easier now. So at the time, full subcategories where there was the implementation was not great. They were implemented as properties on objects, and the Homs were defect to the Homs in the big category, and where you were trying to talk about calculating kernels, it never knew in which category you were working. It was just awful. I think Joel's refactor went through recently, so I should try again. But also another issue was that you had, you were supposed to put a lot of theory in place because before it could work, or if you want to do things properly. So, well, then at that point I was ready to give up, but then I actually discovered there are people who are doing this kind of constructions in GAP. So if you don't know GAP, it's one of these computer programs to do formal algebras, like if you want to calculate group cohomology or things like that. It's great for that. And so these people are actually, there's a GAP package called Categories Algorithm Programming where they are implementing categorical constructions. And I guess they ran into the same kind of problem because they use another construction due to Adelman. And this construction actually is a very explicit one-step construction. It works great in Lean 2. So it's just mentioning, I don't know if I have any homological algebra experts. The construction is so simple that it looks too stupid to work, but it works. So you say, oh, I'm going to just add homology of complexes, except they are not really complexes, they're just two composable arrows. So you have to define homology in a slightly strange way. And then these like complexes that are not complexes, you take them up to homotopy. So maybe I can show you. Yeah, so the good thing is that all the constructions like kernel, co-kernel are very explicit. So here, for example, is the, I don't know if you are following my changes of window. I hope so. Nobody's complaining.
Yes, Sophie, it's okay. Works.
Oh, yeah. So here's the construction of the co-kernel. So there's a morphism here. This is supposed to be the co-kernel. So this is like. And this is checking the universal property. So unlike the other one where it was all like, oh yeah, an object exists because like, I don't know, like some universal, it's much more explicit than the other one. And it's extremely easy to check, and you still have to suffer a little, but relatively. Yeah, I can show you. It's actually so this one is totally implemented with all its universal properties. So you use the composable arrows thing, and the definition of the homotopy is here, and then you have all this universal properties somewhere down there. So just in the end, write it as an equivalence of categories. So the way I stated the theorem is actually the way it's proved. Yeah, this is just a little bit. Yeah, here it is. So equivalence, if you have an additive category C, you construct an abelian category adel C, and then exact functors into any other abelian categories correspond to additive functions from C to the abelian category, and the equivalence is just composing with a functor from C to adel C. That's just a little bit, so something that's not written in informal mass is like about the co-unit of the equivalence. I'm not totally sure what it is, but yeah, I haven't quite worked it out. That's the kind of thing when you formalize something, you discover that not every detail is actually spelled out. Yeah, so that's so the project is available. It's kind of a mess because there are bits of rates construction in it that don't work. And actually it worked because of the way homological algebra is written is really nice. So you can just adapt a lot of the constructions of homological algebra and simplify your life. So one reason I didn't try to PR this to Masslib because I was afraid it actually does a bit less than phrase construction. Phrase construction just adds co-kernels to an additive category, and then it adds kernels. Adelman's construction just adds everything at once. So you don't get the procedure that adds only the co-kernels from it. And I was afraid I was going to be told, oh yeah, this is not general enough for Masslib. But anyway. Right, so yeah, I want to talk about the problems now. So here's the theorem again. And now I showed you like every step of the proof. So can we put them all together and prove the theorem in Lean? And there are a few problems. So the first problem is we can't quite do that, and the second problem is we can't even state the theorem in Lean. Okay, so let's talk about maybe the second problem first. The second, which I called first problem in my notes because I'm okay. So it's a problem with universes. So some of these properties in MathLib, there are two universal properties, and they are not written for general universes. This is actually totally trivial to fix if you just go into the MathLib files and you just change the universes. Everything works. So it's just that whoever wrote them didn't think to just put different universes for the categories, which you should always do, because that the result in MathLib is actually less general than the result in informal math that doesn't assume equal universes. But and this is a very easy mistake to make, of course. So that's okay. I mean, it's I should do a PR, but it's okay. The other problem, the statement of the theorem. So the theorem, it should not be stated like this is inequality. I should say something like all representations from the quiver to an abelian category. The category of arrows for representations from D to A is equivalent to the category of exact functors from A to this abd, and the equivalence is just actually not so clear, but it was constructed. It comes from the other constructions. I cannot actually say that because pre-functors from a quiver to a category don't have a category structure in MathLib. Because natural transformations are only defined on functors, even though they don't actually need the source to be a category. They don't use composition on the source in the definition or in any of the constructions. So no problem, just go to the nattrans file and just fix it. Easy. Okay, so here I ran into the quiver trap, which I fixed actually. Well, I mean, I stopped my code from exploding this morning, but I'm still very unhappy about that, what happened. Yeah, so the slide is kind of explaining. So quivers are actually doing two things. One of them is being categories without composition, and the other one is being directed graphs. And so their arrows are not a type V, they are sort V because of that. And so maybe I can show you. Right, so where is it? I lost my mattrans file. Okay, so I was working with so I said nattrans, you can just generalize. It's like trivial. So I called the result nattrans Q. So here I'm not supposing that C is a category, it's a quiver, but I just literally copied the definition from MathLib and every lemma that comes after that. And I was very happy. I said, well, now I can just state my theorem. So I went into this file that defines the structure of category on the type of functors between two categories. And I just replaced the first category with a quiver. Here is the nice mistake. Yeah, okay. So when you see something like that, I mean, if you're me, you panic. So I tried to understand what was going on, and what's going on is that the type of prefunctors between two quivers lives in this like disgusting universe, because the quivers are like sort, not type. Okay, and if you want to fix it, here. So a quiver is a category without composition, but the analog of a category with humps in type V is a quiver with humps in sort v plus 1. And because of that, if you don't put v plus 1 everywhere, your code explodes. Okay, and that means that if you don't put v plus 1, actually the type of prefunctors between a quiver and a category, you cannot put a category structure on it in mass, even though it is a category. So I don't know what to do about that. Yeah. And I think, I mean, okay. Yeah, so I to say if you just a mathematician trying to formalize something and you run into that kind of error, you lose a lot of time. And I would suggest a refactor. I mean, doing something about that part of the library. Maybe a type synonym pre-category for quivers as categories without composition. Or something. Yeah, I'm not quite sure, but that's, I think, what I wanted to say. Thank you.